questions? Okay, so first thing we can do is get that w prime to show us dw dt. Cross multiply. We want W's on the left, T's on the right. And at this stage, even though when I cross multiply, my goal was just to get the dw and dt in the right places, and they are, but it looks like I already have full separation of variables. So no need to move anything else. W's are already together, T's are already together. Left side is just pretty clean power rule. The right side, a little messier, but easy to spot the U value being the parentheses there. That's true. All right, t squared cancels out. 1/6 remains. We have a rule for secant squared, which is tangent. Tangent of u plus c, I'll replace the u back in terms of e. And I'll bring over the left side here. So w becomes w squared over 2. All right, any questions so far? Okay, so at this stage, we're done with the calculus. Two things left to do: solve for W, solve for C. But the order that you do them in is not. It's really up to you. So I like to clean up a little bit, at least to the point where my equation feels easier before I solve for C. That's just my preference. So I'm going to multiply a 2 through. I feel at this stage, this equation feels easier and cleaner. So I'm just going to pause and plug in and solve for C at this point. That 0 is nice because that's going to force that tangent to 0 out as well. So I get C equals 16. I could go back to my general equation. Now my final step is take the square roots. However, there's a plus or minus that will show up, but these are two separate equations. We got to choose the one that will pass through this ordered pair. So the sign of the y value of the original equation is going to be the sign that you want to keep for your solution.
What is that order?
The reason why is because if I plug 0 into this equation, I've got to get a -4 in return. If I plug 0 in for t, I'll get tangent of 0, which is 0. 0 plus 16 is 16. Root 16 is 4. So if I keep that positive square root, this order pair doesn't live there. So I have to have a negative sitting out here to ensure that I get that -4.
Okay.
All right, any questions with number 5? All right, number 6. Let's get that y prime to show us dy over dx. I'm going to go ahead and move that y to the right side so I can prepare for cross multiplying. So my first goal is make sure that get my dy and dx is lined up. I want my dy on the left, dx on the right. And now we ask ourselves, do we have full separation of variables? And we don't, right? We have multiple things out of place. The y is out of place. The x, ln x is out of place. So we'll do two things at once. We'll just make them swap to the other side of the equation, make them go to the denominator of the opposite side. It's okay to have x's and y's in the denominator as long as we're following our algebraic rules. Integral to both sides. Left side is just natural log 1 over u du. But the right side, we got to go through a little bit of u substitution. We know we're not going to ever replace u with x. That's never going to make the problem easier. Our u value is not the entire denominator either, because if it's the u value is the entire denominator, the derivative will be product rule, and there's nothing that's going to match the result of that product rule. So our next guess is our u value being natural log of x. If our u value is natural log of x, our derivative is 1 over x, and there's a 1 over x waiting for us that should cancel out.
Why it wouldn't be x?
So if you do u substitution, you never want to do u equals x. If you do that, then you're just making a 1-for-1 swap. And then you're basically looking at the same equation with a different variable. And the whole purpose is we want to create an easier version of the problem. So our u value is always more than x.
Thank you.
How many questions will the quiz be?
It'll be like 9 problems.
Thank you.
So we get the x's to cancel out. Ends up being 1 over u du, which is natural log. And the left side is also natural log as well. So we're now up to the equation level. So 2 things left to do: solve for c and solve for y. We're going to wait to solve for c here. So I'm just going to raise both sides. E is the base. That should clean up a lot of things for us. Split up that right side. Place e to the c with c. E and natural log also cancels out, so we can drop all the absolute values because we know c will take in all the plus or minus that we give it. So we're now ready for our order pair. E in for x, E in for y, solve for c. We know natural log of E is just 1, so c is just equal to E. Any questions so far? All right, slope fields. right, so number one, we're trying to match the appropriate slope field that is for dy dx equals x minus y. Now, if we look at x minus y, we can also see that there are some collection of ordered pairs that will produce slopes that are easy for us to find. For instance, if I have if x and y's are the same, then my slope is always going to end up being what? 0, 0, right? So 1, 1, 2, 2, 3, 3, 4, 4, right? All those will produce slope zeros. And if I look at those ordered pairs, where 1, 1 is, where 2, 2 is. So it looks like I can at least narrow it down to B and C because those are the only ones that are giving me a nice collection of slope zeros there. But if I look at these two here, looks like if I just shift one over, my slope is distinctly different, right? So maybe if I pick an ordered pair that is to the right of 1, 1, like 2, 1, 2, 1, or 3, 1, or 4, 1, if I plug those in, if I plugged in 2, 1, I'll get 1, 3, 1, I'll get 2, 4, 1, I'll get 4, 3. So those are all positive slopes. And we see that, at this stage, you can, if you're down to 2, you can look at specific order pairs and see which one will produce the slope, even though you can't tell exactly what these slopes are. These are clear enough where one is negative, the other is positive. And if I plug in order pair 2, 1, I'm getting a positive slope, so I can narrow it down to this. So sometimes, so sometimes if you're able to get it down to 2 options, look for specific order pairs that are distinctly different, and then plug into the differential equation and see which one is going to produce the one that's going to match the slope that you want.
So yeah, it's Austin's birthday today, actually.
Happy birthday, Austin.
Thank you.
300.
It's like 3 points. Give something.
This will be laid out. That's good.
One point very.
That's 1 point for every energy drink.
For number 2, we can see that there's a shift, right? Somewhere around 1 or between 1 and 2, there's a slope 0. Everything to the left of that x value is negative. Everything to the right is positive. So if we can see that, we see that relationship, we can look to see which one is going to meet that criteria. We know x minus 2 squared is always positive, so we know that that's not going to be a good fit because we don't see any. We do see some negative slopes here. 0.5y is only depending on the y value for the slope. So that means positive y value is positive slope, negative y value is negative slope. Okay, but that's not the case here, right? So x plus y, we should get a bunch of 0 slopes here. And for instance, negative 1, 1, or negative 2, 2, or negative 3, 3. That's not the case. Here, x minus y, 1, 1 will be 0, order pair 2, 2 will be 0, 3, 3 will be 0. We don't see that lined up very well. So 0.5x minus 1, I think it's the best fit. This is. Let's check it first.
And then, like, I told us, because I wasn't there.
Straight. If we know it's an exponential decay, does that mess up our initial equation at all? Or
What do you mean?
like if it's a decay, like do we do
Oh,
anything?
no, it's the same. It's y equals to e to the kt.
Okay.
Yeah.
But should we like look for a specific like C or K value, depending on it, that would like kind of show us if we're like, should our C value be negative?
If it's a decay, typically your k value is negative, but
Yeah.
nothing to worry about. As long as, yeah, if you see that relationship y prime equals ky or p prime equals kp, you know it's going to be that y equals c to the kt. Okay, next up, x times y. So x times y, we know that first and third quadrant will give us positive, second and fourth quadrant will give us negative. You'll be the best fit there. And here we can look for zero slopes and slope ones. May have to plug in specific order pairs, but it should be eliminated all the way down to answer choice D here. Let me do a verifying differential equation. Verifying differential equation. This is part of your homework from before, but I'll redo this one. So this is page 4, number 11. So the strategy here is you're going to find your derivatives that the different equation is asking you for, and then you make those substitutions, and then and solve for k. So I didn't mention here for number 11 and 10 and 10 and 11 you're just solving for k. So I'll work through that problem. Okay, so let's make our way down to y. Double prime. A is just a coefficient. Sine of u becomes cosine of u times u prime. Cosine of u becomes negative sine of u times u prime. clean up y prime, and then we move on to y double prime. All right, so let's make our substitutions. Replace y double prime with this expression. Replace y with the original equation. Take out some like terms. Combine some of the like terms here. This becomes 16K. Divide both sides by 16 sine negative x.
Sure. Being 14.
Yeah. This one here.
Yeah.
Okay. So part A is just sketching through that point. So they highlighted the order pair 1, 2, and you're just following the flow of the graph. So you sketch it. Part B, you're writing your tangent line equation. So order pair is order 1, 2. Your derivative is your slope formula. So plug 1, 2 into your derivative, get your slope. Then do point slope form, and then finally plug in that 0.8. So my slope formula is 1/2 sine of pi over 2x times root y plus 7. Replace 1 in for x, 2 in for y. Do some cleanup here. Root 9 is 3. Sine of pi over 2 is 1. 1/2 times 3 is 3/2. Take your order pair and your slope, put it into point slope form, solve for y, and the decimal goes into your linear equation. That will be your linear approximation. Part C, it is known that f double prime is greater than 0, so that's indicating that our original graph is showing concave up. If my graph is concave up with a tangent line that's skimming the surface of that curve, I know this tangent line is always going to under approximate because it's sitting below the curve, so underestimation. Okay, part D, we're cross multiplying first. So set up your fraction in a way where you can cross multiply. As you cross multiply, your dy is going to be on the left. Everything else is originally on the right side. But when we do that, we see that we do have one thing out of place. It's that root y plus 7. So we divide that root y plus 7 over. And then we can then move into our integral process because we have full separation of variables. Y is on the left, x is on the right. Right side is a little bit of u substitution. Left side is also u substitution, but it's just going to be that y plus 7. But we know that we're going to be working towards power rule and not natural log because this is not raised to the first power. This is raised to the 1/2. So I just brought it up to the negative 1/2 at the beginning so that as a reminder that ultimately this is where my problem has to be if we want to do power rule. Okay, replace y plus 7 being our u value. The derivative won't produce anything except 1. And then we're left with u to the negative 1/2, which is u to the 1/2 over 1/2. U substitution on the right, u is power 2x. Cross multiply, solve for dx. Dx equals 2 du over pi. Make that substitution. Cancel out your coefficients, but we do still have a leftover 1 over pi. And sine becomes negative cosine with the 1 over pi in front. And after that, we're just doing a bunch of cleanup. You're deciding how you want to, which order you want to solve for y and solve for c, but those are the two things remaining. So I solve for c first. I was going to get it all the way down to 6. And then my last task is to solve for y. So I have to clean up all this stuff on the left side. So divide by 2, square both sides, subtract 7. This is my relationship. This is how awesome. So there was a second derivative like this. There, from down here. This will be this. So okay, I know we did this yesterday during review session, but I want to do this again. This is the potato problem on page 5. The part A says write equation for the line tangent to the graph of h at t equals 0. So typically when we think of tangent equation, we think of y and x's. We can start off that way, but we just have to make an adjustment with our variables. Notice that instead of x's and y's, it's t and h. So t will replace x, h will replace y. So your tangent equation It's gonna be a better fit if we say H minus H of one equals N times T minus T sub one, but same equation, we just have to adjust for the new independent and new dependent variable. So they give you an order pair of 0, 91. This will be your T sub one and H sub one. We can plug in this order pair into the derivative to get our slope. So if I plug, looks like my derivative only requires the H value, so I can plug 91 in for H, and I get a slope of negative 16. So I have my order pair, 0, 91, and my slope is negative 16. So I'm just putting it into my linear equation, and I'm just making my replacements in the same places that I would if it was in terms of X and Y. So replace T sub one with 0, replace H sub one with 91, replace N with negative 16, and I solve for H. And then you're doing linear approximations. In this case, linear approximation is integer value, but it's okay. Just plug that 3 into your linear equation, and you get your approximation. Don't worry about part B. Part C, we're moving into solving the differential equation. So eventually we want G's on the left and T's on the right. So let me walk through the steps that I did yesterday here. So first step, get your fractions lined up so I can cross multiply. Cross multiply in a way where your dg is on the left, your dt is on the right. And then our next observation is, do we have full separation variables? We don't. The parentheses, g minus 27 needs to move over. Now I'm moving the parentheses, but I'm leaving the negative because I know that I don't have to move the negative over. I just want to move what is essential for the left side. So I'm just moving over the parentheses, keeping the negative 1 on the right side. When we see this, we should see, okay, there's an equal u substitution. My u value is just what's inside the parentheses, but that 2/3 is a reminder that this is not going to be natural log. This is eventually going to just be power rule. So u value is g minus 27. We find the derivative, no leftover coefficient, and we make our substitution here, u to 2/3 in the denominator, but it's out of place. We got to bring it up before we can begin power rule. So u to the negative 2/3 is ready for power rule. Make it u to the 1/3 over 1/3. Right side, -1 becomes -1t plus t. And now we have our general equation. You're free to decide which order you want to do your final 2 steps in, solving for C and solving for G. I find that this is relatively easy spot for me to solve for C, so I'm going to go ahead and do that. 0 in for T, 91 in for G. I'm able to get it all the way down to C equals 12. Once I have C equals 12, I replace 12 in for C. And now my last task is trying to get that G by itself. So I'm going to divide by 3, cube both sides, and add 27. Yeah.
So with that equation in the top right, be your general solution.
Yeah, your general solution can look at a number of different ways. If you want to solve for G first with the C, basically, if the C value is still there, there's a number of different ways that the general solution can look. It can be a general solution with a G yet unresolved, or it can be a general solution with a G resolved. And if that were the case, then this would still be a C value. If you want to wait to the end, you can solve for C at this point and plug in 0 and 91. Okay. So depending on where you solve for C, your C value may be different than mine, but at the end, we should be in agreement.
And then if we need to find a general solution, we will need to give the unit variable by itself.
Self-access. Yeah.
But then if it's squared.
Yeah. If it's squared, then you can leave it as
That's the same thing, isn't it?
Thank you.
Yeah, I just want to point out, sometimes with these differential equations, the algebra can be a little messy at the end. But the emphasis is really on the calculus portion. So if you get the calculus portion right, if you having trouble getting that algebra section done, or you're having trouble getting that C value, that G value, ultimately that is worth less than the calculus portion. And also, it's not all or nothing, right? That's, I'm looking at all your work. If you're messing up at the end, that's pretty minor deduction. Okay, let me know if you have any individual questions.
I have a question here. So it's just like the format.
Same thing.
Okay, so if I write the first one, it would.
That's fine.
Okay.
Mind explaining why we have a single maneuver X national of X? Why shouldn't it be the whole thing? This wasn't it with the derivative.
Exactly, yeah. If the derivative is really weird, and I don't see any pairing that can handle the derivative that's going to come out of the product. So this is too much. Just do it if I move out.
Thank you.
Yeah. Yes. I mean, this is a little messy, but there's the related rates that work into this, but you won't see related rates somewhere.
Wait, continue expression. Can I take the first thing?
Yeah. Okay.
Thank you so much.
You spent the day to.
Yes, yes, I will. I just completely.
Sure.
Thank you. Just cleaning. I felt like.
No, I didn't.
I cut out and it was like, I thought you said that was like.
No.
Okay.
Yeah.
Thank you.
Okay.
I'm sorry.